My name is Brett Zerba. I am an applications engineer with TACO Comfort Solutions.
So, chilled beams. Hopefully you know what TACO is. We are a hydronic HVAC pump manufacturer. We do not manufacture chilled beams. We talk about systems and maybe some of our products going into systems, but it's more for education, and that's what I'm going to try to cover. So please ask questions. Obviously it's a small group, we have 7, 8 people here. Ask some questions if you have some about it. But I am going to get into my goal at the end is to get into a piping system where maybe that can help you save some money when you install this product, when you install this type of system. So here's today's agenda, right? Building suitability. What type of buildings is a product like this good for? I'd like to start with that just to kind of clear the air, because there are some that it's probably not really that good for. And then what type of chill beams are there? There's probably 3 types, but we'll get into all of those. One is more common than most, but nonetheless, we'll talk about that. And then water versus air efficiency, right? There's been some other classes that RPA has sponsored, and we talk about water compared to air efficiency. And that's what one of the big differences potentially is for this type of system, this type of product as well. And then some advantages compared to a VAV system, right? Many of you may be familiar with the type of VAV systems. Well, there could be some advantages using a system like this. And then the low flow piping system. That's the system that I really want to spend some time in. And I should have time, we'll get through this pretty quick probably, where I can actually design a system utilizing some software that's available on the free of charge at our website. So we'll go from there. So here's some buildings that favor a chill beam. And I'm going to show you some pictures of chill beams in case someone has never seen one, or some radiant piping. That's what this is. Instead of radiant heating, maybe in the floor or snow melting that some of you may have heard of, this is for radiant cooling, okay? One of the key items is moderate, high sensible load densities, okay? So that's something to consider. Some zones with moderate, high densities. Also, high rises, existing buildings with induction systems. That's a potential that we've seen in the marketplace. And there's a lot of chill beam manufacturers out there as well. We're partners with some of them, and maybe you folks have done some business with some of them as well. Another one, and we have a training facility. Dwayne and I were talking about it. Dwayne's the cameraman, that's why I keep saying Dwayne, a good friend of mine as well. We have a training facility at TACO, and we have our big classroom. It's a 63 seat classroom, stadium style. That actually was the architect worked for Harvard University, or they did projects for Harvard, so it's kind of tailored after one of those. And so we have 9 active chill beams in there. Very, very quiet. You cannot hear a pin. You can't hear the air coming in. It's very, very quiet. But you're comfortable, especially in a degree day, right? We're in a pretty humid climate out in Cranston, Rhode Island, and not as humid as maybe some of the climates you folks are used to in different parts of the country. But nonetheless, in July and August, we do get some issues there. And then this bottom one, I don't know if people are still seeking LEED or green certifications. It's a big energy saver. It can be a big energy saver, so that may be another reason to look at this, right? Some favors for active chill beams. Here's a few that are less favorable. And I can't emphasize the first one enough. Old buildings, leaky windows, leaky construction. If there's ways for humidity to get into the building, that's not a good situation for one of these type of systems. Stay away from it. Go back to your more traditional type of system. If you maybe not in this gentleman was talking beforehand, he's in San Diego, maybe not in his area, it's not as critical, but if you're in a humid climate, that's very, very disadvantage, big issue. It could be a big issue. And then if you have a relatively low sensible density, that could be another reason not to use this here. So you want to be around 70% in that regard. So And then if there's high filtrations, high latent loads, if there's a high latent load in a building or zones, you don't want to use this as well. So, but that leaky windows, and really, I've worked on some projects with some engineers that we work with our reps, where they were going to put in chill beams, and they were going to have operable windows. And there's ways to shut the system down and add complexity. I tell people, I used to be an engineer for a consulting firm. I like to keep things simple, but you add complexity to a system, you could be asking for trouble, right? Yes, you can open a window, boom, it's going to shut the system down, but that's just adding complexity. So people can tell you can do it, and yes, you can, but it's just a personal choice. I probably wouldn't recommend doing something like that. But again, others would. Keep in mind, I don't sell the chill beams, so that's something to consider. And then there are some out there with drain pans can be considered. So we'll talk about that when we go into some of those. So there's favorable ones and less favorable ones, something to consider as you look at it. 3 types of chill beams, or radiant cooling type of systems. Chilled ceiling, and really all that would be, and this kind of started in Europe, or it did start in Europe. A lot of the buildings back a long time ago weren't chilled, weren't air conditioned, so all they did was put some pipe up above the ceilings, right? They didn't have room to put anything up there, so that's really what a chilled ceiling is, and I'll show you a picture of that very shortly. Then you have passive chill beams. Passive chill beams, and they're just, I'm going to show you some pictures of those. Those are just for cooling. There's no air induced into that. And probably most projects nowadays have what they call active chill beams. Active chill beams, and I'm going to show you some pictures, but that's a system where the primary air is induced or brought into the chill beam. The dry primary air. So here's a kind of a picture. Unfortunately, and you can see on the bottom right, it's dropped down, and it just has some tubing on it. Maybe it could be copper, it could be some plastic tubing, and that's just above the ceiling. And that's that chilled water that goes into that coil has to be above the dew point. If you notice up in the top left-hand corner, right, it says 59 to 62 degrees. It's so important. If it's not above the dew point, you will get dripping. You will get dripping or some moisture in the system. So that's one of the critical parts of it, no matter what type of radiant cooling you're putting in. And that's why a lot of people are scared of this type of system, especially in very humid climates. Passive chill beams. These are only for cooling. And you can see the piping at the end. See the piping at the far end? So that would be a supply of chilled water and a return coming out of the chilled water. And then there's your space temperature, relative humidity. But again, the water that goes into there, that cool water, chilled water that goes into there, has to be above the dew point. We're going to talk about some controls and some possible controls for a system like this as we go further. And again, this is only for chilled water. And a lot of times you can see, it's a simple sketch here. You can see it's hanging below the ceiling, right? And you might have some perforations, similar to the grates up here. And then, and I'm going to show you how so here's the actual flow in the chill beam, and you can see the cooling comes down. So it's very, very subtle, very a slow type of setup. That there's what you could expect from a passive chill beam. So here's let me go back there. You can kind of see what you could expect in a room. If you ever do get in a project working with a system like this, work with a chill beam manufacturer. Find one that you're comfortable with, and they have a lot of programs that can help lay it out in the building, and that, or the zone, or the room. And that's what we did, our mechanical team, when we designed our building. And they help you. They come with lights now, drip pans. There's all kinds of gadgets that the chill beam manufacturers have. But there's kind of the gentle flow you could expect from a passive chill beam. Very, very comfortable, very quiet. Here's the more probably prevalent one now. What we call is the active chill beam. and you see the little connection on the far left, that's where the primary air comes in. That's where the primary air comes in. The dry primary air comes in there. And this one happens to be a four-pipe. So it can be heating and cooling. And so there's actually some, heat exchangers, not heat exchangers, there's coils in there, and about roughly 2/3 of the coil in a four-pipe would be cooling, and 1/3 would be heating, roughly. That could be a little different for different manufacturers, but that's how it's set up there. So the ones at our factory that happen to be the Dankos, that's the company we work with. They're out from, we're in New England and they're in New England, but nonetheless, that's very similar to what we use with them. And we do use it for heating in the winter and cooling in the summer. I had to borrow this, so here's kind of the engineering associated with this. You can see right here, right, the primary air coming from the energy recovery unit, right? There's different temperatures that you might be going in there. It's very gentle, very small. That it's going there. You're going to see a flow pattern, air flow pattern very shortly. And there's the induction. Let me get so the air comes in right here. See how it comes in? It goes through some nozzles right here. Induces the air to come up here, and then this gentle air comes down, and it just falls down into the zone. And like I said, that's why in our big classroom, we have 9 of those beams, and they're all spaced properly, so the air comes down, and it gently falls down into the our ceiling isn't this high. It's probably half as much. I would say it's at least 12 feet anyways. It's stadium, so it might be 16 down by the instructor, but nonetheless, there's your operation principle for the active chill beam. So here's what you could expect in the flow pattern in a room with more than one chill beam. Pretty straightforward, pretty gentle, very quiet. No fans, no moving parts. As a matter of fact, our facility's been up and running now for 10 years. And we've only had to just vacuum it out. You really don't have to do much maintenance to them at all. Not like a fan coil or something else in the room. Very gentle, very clean. And when we started it up or turned it on, we were people were amazed. They said, "So how do they work? There's no fan blowing?" No, that air just comes in and just induces the hot air up, and the cool air comes down. Very straightforward. This is the dedicated outside air unit. The energy recovery unit, whatever you want to call it. It's very important. So you need to design the air that gets to those chill beams to be very dry. It has to be very dry. So here's the exhaust air coming out of the room, right, out of the zone, and that goes out here. But the wet air, right? Maybe not for, even Vegas. Well, no, it's pretty dry out in here, but for Miami, for Houston, places like that, even Rhode Island, right? This wet air comes in here. It has to go through a filter, and it also has to go through a recovery and a heating coil to get the dew point out, and then to cool it back down before it goes into the room. So it's going into the room very dry, around 43 degrees dew point. So very low, dry air when it goes back in there. So there's a little difference of work with the DOA unit, but nonetheless, you do have to take that into account when you design it. Here's an actual picture of now we're a manufacturing company. Hopefully you folks have visited our booth, you know us. We're the green pump folks, right? We're not the red guys, not the blue guys, the green guys. That's what I like to say. But this is our training facility. Dwayne and I were talking about it just a little while ago. This is our training facility, about 10 years old, right? So the owner of our company, the White family, put a lot of money into putting a training facility in so we can bring folks like you to our facility and train them and display some of the stuff I'm talking about. And up here is some of those chill beams, and up here is some of those chill beams. Okay, so that is a type. This is a living laboratory training facility. So that's a picture of an actual application or where this is. And we actually have a combination of these radiant cooling type of setups. Right up here, you can actually see a little cutout. This is just the pipe. So that's just the chilled ceiling. So we have that on display. Back here, you can't really see them. We have passive chill beams near the windows, and then these are the active chill beams. So we have some combination there to kind of display it all. And that's what we've done. And here's another thought process. In the afternoon, these are full ceiling windows, so we have 4 of them, right? You can only see 2 here, there's another 2 around the corner, or around the corner. In the afternoon, that sun comes in, barreling in, right? So we actually have shading. Sometimes you can overpower from a sensing point of view, so we have a shade or a blackout, so you can cover that up if the individuals get uncomfortable. But usually it doesn't happen, but it's usually just to block it. And then in the winter, when these are heating, we also have some baseboard above near the windows as well. So it's a combination system. When you start thinking about what you need to do to make sure the room's comfortable, that's what we're doing here. So that's our classroom. We have a bunch of other classrooms. That's the only stadium one. The other ones are kind of like conference rooms that can be opened up, similar to this, right? This could be closed up, opened up, or whatever, and whatnot. So that's our chilled ceiling that we have there. Water versus air efficiency. I talked about doing that. So there's different ways to cool buildings, right? So she was mentioning water source, air pumps, VAVs type of systems. Well, to cool 12,000 BTUs, 1 ton of cooling requires around this much air, this much water. So here's your ductwork size. You think about savings, right? 10 by 12 compared to a little 3/4 inch pipe. Big savings right there, possibly. The efficiencies of water versus air. And this just shows you, if you start going through the formulas, and I don't really like to go through the formulas, they're up here, you can take a picture of it, but 10 times as much horsepower as water horsepower to cool that room, to cool that zone. So that's a big savings right there. So, Taco's a manufacturer of HVAC hydronic equipment. We like to talk hydronics as much as we can. And if you can show people how to save money, save energy, horsepower, less horsepower, and get the ball rolling in that direction, that's what we like to do. And we think it's a very good alternative to other types of systems that are out there. Here's some of the savings compared to VAVs. The air handler units can be a lot less because you don't have to, well, some of the things you just seen there, but you don't have to dry all the air. You only have to dry that air coming into the zones. It's like it's about 30%, 70%. Smaller ductwork, we just showed you that, right? You only need to get that smaller duct coming into the air handlers. Much smaller ductwork. Less noise, right? VAVs, you can hear them come on. Maybe not in this room, but you can hear them come on. In our zones, you don't hear that air coming in. It's very gentle when it comes in. In other industries or other ways to heat and cool buildings, maybe VRF, they talk about how quiet their system is. This system is just as quiet. So maybe for schools or museums or whatnot. We actually have a project that our rep got involved in Miami, Florida, and it's in a school. And the people were comfortable, the teachers were comfortable, the staff was comfortable, but they didn't think the system was working. So they call our rep up, and a lot of you folks get phone calls, right? So, okay, you start asking questions. You don't think it's working? Is it cool? Oh no, we're comfortable. So it's not working? Okay, I'll come over. They didn't hear anything. So they didn't think it was working. And so, it's a little hand-holding sometimes. I can see somebody chuckling up here because he's probably getting the calls. Maybe not that similar, but stuff like that sometimes you don't know how to answer them, right? I know how, unfortunately, I would answer it and then I get in trouble, so I got to be careful how I answer things like that. Lower maintenance, right? You don't have, in the zones, right, you were talking about heat pumps, right? There might be some maintenance issues or servicing with heat pumps, although that industry has come a long way, and they have some great products out there, and I work with a lot of those folks because it's hydronics, and a lot of folks out there, but these, in the rooms, the chill beams do not require much maintenance at all. And then, this is something that folks don't actually consider too much, but it can have less electrical infrastructure costs. Infrastructure, whatever that word is. So you should be able to save some horsepower at the beginning of the project as well, and less fan horsepower as well, and lower operating costs. I can't emphasize that enough, right? You're not blowing as much air. You could be saving a lot of electricity. And we were able to get LEED certification for that room, or that, it was a 24,000 square foot addition, offices upstairs, classroom, and the entryway downstairs. But nonetheless, we were able to show a big energy savings that helped us get quite a few points in the LEED certification. Some of you may know that whole process and what all that is for. So nonetheless, we were able to do that. Another thing you got to be careful of if you get involved with one of these projects: entryways, radiant cooling. If you open that door, right, and a big inrush of humidity can come in, you gotta take that into account. You're gonna over stress the chill beam system, radiant cooling system. So you need vestibules or some other type of system right at the beginning. So at our facility, we have a vestibule that's handled by a heat pump or a fan coil. We have two big entrances in the front and back. So you got to make sure you take that into account. So that's some other things we've learned when we work with engineers over the time. Matter of fact, one of the first systems that we did was at our facility in Milton, Canada. So we took care of the entryways, but we forgot about the door that goes out to the production area that wasn't treated. So that we had to go back and take care of that area. So things you learn as you design these systems. So stuff to make sure you take into account. So I'm going to talk about the piping system. All right. So on the brochure it says ways to save money with this type of system. Okay. So this is you know, the rest of it was kind of an introduction to radiant cooling. This is a different type of piping system, a different thought process, right? So your traditional cooling system, right? You know, it's different than a heat pump system. Here's your low temperature chiller, right? With a 10-degree delta T, 12 degree, 14 degree, whatever it is, delivering cold water, right, to the area. Fan coils, dedicated outside air, couple of pipes, boom. You need that. You still need that in a chill beam system because you have to dehumidify the air coming into the building. Then you also need some type of distribution of warm cold water. What I mean by that is something above the dew point. I'm showing 58 degrees, it can be 55, it can be 60, it can be 52, you know, but it's above the dew point. It's not 42, right? It's 58. So there's two piping systems all of a sudden. Complexity, right? I talked about complexity and how I like to keep things simple. So I've seen systems, I've seen documentations where there's two chillers, one with low temperature. Think of the money, right? Cost going up. Low temperature, high temperature, distribution system. A lot of pipe, a lot of complexity. Most of the time, most people would probably just use this one chiller with a heat exchanger and more pumps. We like more pumps, right? Especially if they're green. But nonetheless, the complexity of the piping system can raise the first cost, up, maybe where people get scared, right? And that is one of the items that you really have to work with when it comes to one of these systems, right? You can see the complexity here, right? I need to get cold water to the dedicated outside air unit, air handler. I need to get cold water to fan coils at the entrances, like I talked about. And then I need to get warm cold water to the zones, to the chill beams. What if we could do it a different way? Here's the low flow radiant chill beam injection pumping system that we've worked with folks on a lot of projects. When one of these projects is over budget, they will work with our rep and us, someone like myself or someone else at my office, and we will do a layout like this for them. So now we have one chiller. Instead of instead of taking care of the temperature in this room, in the mechanical room, we're going to do it at the zone. We're going to do it at the zone. And there's other systems similar to this out there. We have a different type of approach. But notice, instead of 1, 2, 3, at least 4 pipes, and this is just chilled water, right? I'm not even talking heating right now. We only show 1 pipe going around. We only show 1 pipe. We are mixing at the zone. This is our low flow block right here. So somehow you got a supply and return getting into the dedicated outside air, right off the chiller, 42 degrees, takes care of the humidity, the dew point. Then we mix at each zone. I'm going to get into the details of what this contraption is very shortly. And then at the fan coil entrances, we will just have a little circulator pulling off of this loop to get into the fan coils. Get into the fan coils. So this is the low flow injection pumping system. So here's some of the details of the, it's a little hard to see, I apologize. Some of the details, so, Christ, I did a terrible job with this one. But nonetheless, these are the chill beams. Now I'm showing one of these for 1 chill beam, but at our factory we have one of these contraptions, our low flow block, for 9 chill beams. For 9 chill beams. So you have one for a zone, not for one for a beam. So you got to keep that in mind. And you can see we have one and it mixes here. So the water goes in, variable speed circulator, injection circulator, goes through the zone, thermostat controls this, humidity controls this, comes back in as the water warms up, we inject some cold water right here. So we're mixing right at the zone. We're mixing right at the zone with our low flow block. And we can sell the controls. We offer the controls to the folks to do that as well. And obviously, this is for teaching purposes. Please don't think that this is how simple the mechanical room is. I understand there's probably parallel pumping or a backup pumping and other control valving and shut-off valves and all that. This is just for this type of documentation. So I wouldn't want to just take a picture of this and install it. So just keep that in mind. This is our low-flow injection pumping type of system. This contraption right here is our twin T. This is our twin T, and that's what this is. So this is just a fitting, makes installation a little easier, right? And the supply and return going off to the zone is at the same point along here instead of 2 closely spaced T's. It replaces 2 closely spaced T's. That's what that setup is doing right there. And this is this is the only proprietary part of this type of system. So just keep that in mind. That's the only proprietary part. You could actually do it with 2 closely spaced T's just as well, right? So you got a decoupler here. You know how a little decoupler there instead of the twin T. So that's the only proprietary part. But we do have those. We stock them up to 8 inch. But if you get bigger than that, we can fabricate them if we need be. We don't do that too much. Here's a picture of the low flow injection pumping mixing block. Okay, so actually if you go down to our booth, you'll see some, these are actually made at our foundry in Vietnam. The stainless steel, we have a stainless steel foundry in Vietnam. So the zone circulator is constant speed, right? This is a TACO circulator, very reliable, very quiet, right? Constant speed, gets out to the chill beams. And that, so the thermostat and the humidity sensor controls this, and as that temperature warms up, so we have a thermometer on this pipe, as that warms up, this pulls off some cold water to bring it back in. So we're injecting, it's injecting pumping, excuse me. Some of you are probably familiar with that, with other type of setups or whatnot. So that's a variable speed one. It ramps up very slow, it injects it right in until that return water gets back down to where it has to be. So that's the type of thought process we have. And when you install this type of system with our controls, we've seen first cost go anywhere from 20 to 40% less. With the controls, 20 to 40% less. It depends on the project. You really need to work with the contractor and make sure he's comfortable, because it's different, it's new, it's different, but nonetheless something to consider there. So here's one of the setups that we've seen. Okay? So if you look here, I see 2 red pipes. Right? 2 red pipes, 2 green pipes, 2 blue pipes. 6 pipes. 6 pipes. So you have a supply and return for heating, right? To get to the chilled beam. So start thinking about cost. You have supply and return for heating. And there's that baseboard that I was talking about near the windows. And then here's your supply and return, getting to maybe a 6-way valve or some type of control valve or whatever to get to the chill beam, as well as to your energy recovery unit. So that has to go around the building. Then you have the warm cold water. That just doesn't make sense. I say it so many times I get confused. But this is warm cold water, so that's 58 degrees, 55, 56, whatever, above the dew point. Right? And you can adjust that as it goes, and we have variable speed pumping. Now you got that water going around the building, right? And going over to a 6-way valve or something to the chill beams as well. That's all it services, is the chill beams, the radiant cooling. And then you need cold chilled water to go around to get to fan coils or to your energy recovery, the dedicated outside air unit. So you start looking at it. So that's option 0 that a lot of people have. Here's that primary air, right? Here's that primary air. You can see our relativity humidity sensor, primary air dumping back into the room. Here's an alternative way to do it. This is the, like I was showing you, an alternative way to do it, right? Option 2. So this has that primary air coming back, right? Here's our controllers, right? We actually have a controller for each zone. They can all tie together. Here's our primary air coming back. We have one hot water going around for the baseboard, right? Pulling off. One hot water with the radiant mixing block for the heating for the chill beam, and then a cold water mixing here, right? It goes out at 42, but when it gets over to here, it's 58, at least a few degrees. We do it 5 degrees, but other people do it less, above the dew point, and then you've got connections running out to the energy recovery unit for the coils in there as well. So that's a potential savings. Oops, I went back. Right, you start doing piping, right? I mean, if we have a contractor in our group, you know how much you charge per foot of pipe or whatnot. You can see some of the savings here when you look at this low flow type of system. Here's another way you can do it as well. This is option 3, where we actually put a VAV box and control the primary airflow into here. So we have, and I would recommend that for a big classroom like ours, or a big room like this. For an office or something like that, you probably wouldn't need to control that airflow, but we have seen people do that. You can still see the piping system is the same there as well, so something to consider. I'm going to design a system using our software. Any questions?
Does your mixing valves just pull in the hot water? So you have to have a chill beam system with a heating system, because that your mixing valve is using water within your system. If you have to raise the temperature.
Hold on. Oh, I took it off. Let me bring that back up. I want to make sure I answer this properly. Scared myself. I'm pretty good at doing that, though. All right, so your question was about the hot water?
Well, so the mixing valves to get the water back up above the dew point.
Yeah.
Okay. So what does it mix with? Where's the water, the warmer water that's mixing with to get it up to that temperature?
All right, so at the zone, right here, right? This water here there's no chilled water in the system. The chillers aren't, we haven't pulled anything off of here, so this is zone water right now. It's ambient temperature when we start it up. So it's already warm, all right? And then it starts going through here at that 58 degrees, 60 degrees, 55 degrees. And then as it warms up, as it cools, it does its job, this one turns on and brings cold water into it. So it's before the system starts, it's already above above that temperature in the zone. And then the hot water Most chill beam manufacturers don't want 180 degrees at their units, so you probably would want it at the baseboard, but here we would cool it before we put it into the beam. We cool it before we put it. Did I see another question?
Yeah. So I'm more concerned or wondering how the twin T's work. So I'm looking at like the hot water coming from the very bottom. We're coming into 180.
Twin T, you said? No?
Yes.
Yeah.
Yes, twin T. So you're at 180 because you go coming out the page. And then you go into the radiator at 180.
Yeah.
Comes out at 160. It's done some work, so it's lost some heat. And then it feeds back into that line. And it continues going up your page. So in my normal piping systems, I still have two lines there.
Right.
On my
So,
wall.
yep.
And same thing on chill, but just,
There is a cascade of temperatures.
okay.
So, this,
So in that case, it would be 160, call it, going to the,
you get a fraction.
yeah.
So I'm going to make up some numbers, right? So maybe I have 100 GPM in here. I only pull off 5 GPM for this.
Okay.
So yes, it's going back in 20 degrees, 160 back into here. So instead of reducing it to 160, it only reduces it down to 178, maybe
Because you're only
128.
mixing it.
And then, we got to control the flow rate to make sure that cascade doesn't go crazy on us.
Yeah.
That's, but great point, great
Yeah,
point,
yeah.
for sure. Little side story here, but what they did at our factory to keep the place open during, during COVID, well, we're still in COVID. Anyways, it was incredible. They had an A team and a B team, and people from the shop, people from the offices were helping production. A manufacturing facility, you want to make things as close together as possible to make things go quicker. Well, guess what? When COVID hit, we had to spread everybody out. It was totally the opposite thought, but what they did at our facility to keep production going. And I'm sure there's a lot of other stories out there of other places that did very similar things as well, but God bless them because that was fantastic.
And what do you guys call the secondary pumping system? I think they used to call them tertiary. I'm showing my age, but
Low flow?
when you put the pumps in the zone.
Load match.
Load match.
Load match. That's for just the traditional systems.
That's what you guys call load match pump,
Yeah.
matching pumps.
Yep.
Basically.
Is anybody doing just the passive radiators?
Just the what?
Passive radiators without moving air around?
Yep. There are people out there. You still got to somehow you got to get air into the zones though. So yeah, but there are systems out there. Usually it's probably an under airflow type of system because it works best. It helps things get in there. But yeah.
Like in fresh air, but you're not,
It still has to be dehumidified. The air has to be dehumidified.
well, it depends on the radiator.
Right. Oh yeah. Right. Right. Yeah. You live in a different area. You live in San Diego-ish.
Yeah. So if you don't have to do that, the radiant cooled
Right.
radiant panel
Yep.
could function, and you'll get some convection off that anyway, right?
Yep,
It's
yep.
air circulation. You could facilitate that with a low-speed ceiling fan or something like that too.
Yeah, it helps move it around.
Yeah,
It helps move it around. Say,
because then you do that with getting rid of stratification in a radiant floor system.
correct.
So it's kind of a similar thing.
The each one of those chilled beams I talked about, right? We had just the chilled panel, the passive and active. Each one of them, you only get so much cooling out of the first one, then you get a little more out of the second one, and then you get a lot more out of the third one when you go look at BTUs. So that's why the active one is probably more prevalent because of the air coming